Okay, welcome back, everyone. Now we proceed to the last talk of this morning. I'm pleased to introduce Francis Bischoff, who will talk about representations of weighted homogeneous groupoids.
Okay, thank you. Can everyone hear me? Okay, great. So I'd like to start by thanking the organizers for the invitation and this opportunity to speak. So I changed the title of the talk. What I want to talk about is some very recent work, which is about studying flat connections. So we've already seen several talks already about flat connections and their moduli spaces. So I'm also going to talk about this, but in a slightly different setting. So for me, the connections will be holomorphic. They'll be on higher dimensional manifolds, and they're going to have singularities as well. So, and what I want to explain is some kind of very explicit normal form theorems that we can get for these flat connections, and they lead to explicit descriptions of the moduli spaces. So I thought I would start with something very basic, which is just linear ordinary differential equations on the complex plane with Fuchsian singularity at the origin. So this is equations of this form here. So here S, you can think of it as a column vector. A is a holomorphic matrix. And yeah, so we want to study these equations. And basically, because of this Z here, the solutions to this equation, generally, they are singular. They can have a pole at the origin. And the solutions can also be multi-valued. OK, so and when we're studying these equations, we want to study them up to an equivalence, which is gauge transformations. This is also very basic. We just imagined that we're doing maybe a coordinate change. So instead of S, we replace it by an invertible matrix times T. And then we plug this into the equation. And T will satisfy the same type of differential equation. But this new matrix B will be related to A by this kind of well-known formula of gauge transformation. So this is, I think, a very simple but very interesting type of equation to study. There's lots of people who have studied it. So I put some of the important people, but there's many more. And I think maybe the most important thing is the following kind of fundamental theorem, which is telling us how to classify these things up to gauge transformation. So I called it the fundamental theorem. And what it says is that you can always find a holomorphic gauge transformation which puts this matrix into this following form. So here, S is a constant diagonal matrix. And these NIs, these are nilpotent or upper triangular matrices. And they satisfy this following equation. So the kind of the coefficient of Z to the I, it satisfies this equation that if you bracket it with S, it gives you I times the matrix. And I think one useful way of thinking about this is that S plus N0, that's like the constant part. This is like the linear approximation. And this is what you would kind of expect to get in general. But if kind of S is kind of tuned just right, then you can get these extra terms which are kind of the resonant correction terms. And they're occurring here. You can see they're eigenvectors for the adjoint action of S. And just to recall, the eigenvalues of the adjoint action are the differences of the eigenvalues of S. So these terms can only appear if two eigenvalues of S differ by a positive integer. OK, and the second thing that I want to point out is this is an observation that I think Levelt made in a paper in the 70s, is that you can think of this as defining a Jordan decomposition. So first of all, if the higher order terms are not there, we just get S plus N0. This literally is the Jordan decomposition of A. But what he explained is that this, it has a meaning that's kind of invariant. It doesn't depend on gauge transformations. You can kind of split it up into semi-simple and nilpotent part. So this is something that hopefully I'll get to by the end of the talk. Let me just check. How long until when do I have? 58? OK, perfect. OK, so this is the fundamental theorem, and this kind of has implications for the geometry of the space of these equations. In other words, the moduli space. So I just want to briefly explain this on this slide. And yeah, so a lot of people have kind of, I mean, especially Deling and Simpson have contributed to this, but I think the place where it was really made crystal clear in a really general form was in a paper of Bolsch. And what he explained is the following. So I need to introduce a little bit of notation. So I want to fix a matrix R, and I've written it, I've kind of decomposed it. X plus IY is the semi-simple or diagonal part, and N is like the upper triangular or nilpotent part. So I'm going to fix this, and this determines a bunch of stuff. So it first of all determines, and let me give just the simplest example. So R equals X equals this. So this will determine, first of all, a parabolic subgroup of matrices. In this case, it will just be the upper triangular matrices. And it also defines a levy, which is the centralizer of X. In this case, it's just the diagonal matrices. And this levy is a subgroup of P, but there's also a projection map, like this, which in this case, we just project off this component. And then the final thing that we have is we can take this element and exponentiate it, and we take the conjugacy class in L. Okay, so then what Bolsch explained is that the moduli space of these equations, where A of 0, the kind of the constant part, is in the adjoint orbit of R, so it's conjugate to R, then this moduli space is isomorphic to the following quotient. So it's the quotient of a space XR modulo the action of the group, GLN. And this space XR, you can think of it as like the differential equations where we've maybe fixed a trivialization at the point 1. And it consists of the following. It consists of two things, a matrix M and a group P. In this group P, it's going to be conjugate to this fixed parabolic. And the matrix M is an element of P, and it has the property that if you project it to L using this map, then it lies in the conjugacy class. And you can think kind of geometrically, we kind of have the singularity. M is like the parallel transport around the origin, and P is kind of telling us about the growth rates of the solutions to the equation as we drag them in. Okay, and then what Bolsch explained is that this space, XR, it has the structure of a quasi-Hamiltonian G space in the sense of, let's say, the moment map is given just by projecting out M. It's a map from X to G. And this was kind of related to shifted symplectic geometry by Safronov. He explained, well, if we look at G mod G, kind of G acting on itself by conjugation, this is a stack which has a +1 shifted symplectic structure, and this map of projecting out the monodromy is a Lagrangian structure. Okay, so that's just what I wanted to tell you as kind of some background or motivation. So now I want to generalize this picture. So what I want to consider now is flat connections in higher dimensions. And they can have singularities along a hypersurface. In this case, I want it to be this curve here. So this is a curve defined by this equation, x squared equals to y cubed. It has a singularity at the origin, so it has a cusp. So I want to consider flat connections that have a singularity of the simplest form, called logarithmic, along this curve. Okay, so that's what I want to do. So you can kind of write down the general form of one of these things. So here f is this function that cuts out the curve. And a general connection with the logarithmic singularities, it looks like this. So the kind of the two parameters that you can choose are these holomorphic matrices A and B. And in order to be flat, they need to satisfy this differential equation here, where E and V are these two vector fields that are kind of, chosen. Okay, so there's kind of two perspectives on this. One of them is we can just think of these as flat connections, but they have a singularity. The second approach, which I think is popular in this community, is that we replace the tangent bundle with a Lie algebroid, which is kind of specifically adapted to the type of singularity that we're interested in. And then we think of these as smooth flat connections, but for this Lie algebroid. And the one in this case is the so-called logarithmic tangent bundle. So I guess there's a little bit of a debate between notation, but I guess what some people call B tangent bundle, it's the log tangent bundle. Which I would write like this. I guess this terminology comes because of the work of Melrose on the B calculus. And this one, it comes from algebraic geometry, they've been studying these things for many decades. Okay, and the way that it's defined, you just take the vector fields on the space, which are tangent to this submanifold D. In this case, this is a Lie algebroid which has a basis given by these two vector fields that I chose, E and V. And if you take their bracket, they have this relation. Okay, so I want to make kind of an important point here because we've seen examples of this log tangent bundle already in several talks. And we kind of know that they're locally free when D is smooth. And I guess in the last talk we saw when we have simple normal crossings, we also get a vector bundle. In general, this will fail. For a general hypersurface that can have singularities, this log tangent bundle it might just be a sheaf, it might not be locally free. So this was a situation that was kind of studied intensively by Saito in the 80s. And he found the following very nice criterion to detect whether a submanifold has a locally free log tangent bundle. These are called free divisors. And the criterion is very simple. You just take, say you're in n dimensions, you take n vector fields that are in the logarithmic tangent bundle, or then you wedge them together. So those will give you a function times like the volume form. And the condition is that this function, it needs to be a reduced equation for the submanifold. If you can find this, then you're guaranteed that it's a free divisor. So, I mean, we can just check if we want in this case that it works. But there's also a general theorem which is in dimension 2. A curve in dimension 2 is always free. That was proved by Saito. Okay, so yeah, so we're interested in studying these types of connections, and the result that I want to explain is a normal form for these things, and it's given as the following. So it's kind of the generalization of the fundamental theorem that I explained at the beginning. It says that you can find a gauge transformation that puts the connection into the following form. Here S is a constant diagonal matrix, N is nilpotent, and B is just holomorphic, but they have to satisfy this system of equations. So you might think that this is, I mean, we started with one equation and now we have three, but actually this is a lot better situation. And let me just focus on the first equation and explain what's going on. That's the equation that if we apply E to B, then that's equal to B plus the bracket of S with B. So E is this vector field, the kind of the Euler vector field, and it defines a grading of the coordinates, x and y. So x has degree 3 and y has degree 2. And so we can take B and we can consider its homogeneous coordinates of all the different weights. And what this equation says is that the kind of the weight k component, B sub k, is an eigenvector for the adjoint action. So that's the kind of the same equation, I mean, that's the same condition as we had above. So this is actually kind of a collection of eigenvalue equations. And this kind of, I mean, because S is a finite dimensional matrix, it has finitely many eigenspaces, this immediately forces B to have only finitely many weights. So it's a polynomial, and the space of them is a finite dimensional vector space. So this equation, it defines a finite dimensional vector space. And it's the same thing for the equation for n. So the kind of the upshot is that if we fix f, then the flat connections that are parameterized, and we look at the flat connections parameterized by B and N, then, well, the first equations, they define a finite dimensional affine space. And then the last equation, which is quadratic, it cuts out inside of here an algebraic subvariety. So so we get a nice algebraic variety that parameterizes connections. And you can also look at the kind of the residual gauge group, the gauge transformations that preserve S, and for very similar reasons, this is a finite dimensional affine algebraic group, which acts nicely on the space. So the result is that the moduli space of flat connections with what I'm calling semi-simple residue conjugate to S, it has the structure of an algebraic quotient stack. Okay, so that's kind of the first example. So I want to explain one more example of a normal form theorem in dimension 3. So for this, I need to tell you about a very beautiful family of divisors, which were discovered by Sekiguchi. So Sekiguchi, he studied these logarithmic tangent bundles in dimension 3, and he classified kind of a very particular kind of them. And in his classification, he found 17, which I've put here. I only put 16, but that's because I couldn't fit 17 onto one slide. So I've just picked one at random, and I'm going to tell you about this one in detail. So this is, and I just picked this one at random. I could have picked the other ones. Okay, so this one is it's given by the vanishing of this function, and it kind of looks like this. So we want to study the connections that have poles along this thing, and we're going to study them in the same method by looking at the logarithmic tangent bundle, and then looking at the connections for that. So the logarithmic tangent bundle, in this case, it has this explicit basis, which satisfy these bracket relations. And so if we want to study the flat connections, well, we should choose, let's choose the dual basis of log1 forms. Then a flat connection is just given by something like this. So 3 matrices now, A, B, and C. And in order to be flat, they have to satisfy this system of equations. And again, in this case, we get a normal form theorem. It says that the holomorphic gauge transformations have to take the following form. So after a holomorphic gauge transformation, the connection can be put into the following form. So S is a constant diagonal matrix and is nilpotent, and then you have B and C, and they satisfy this system of equations. And again, looking at the first 3 equations, we get a finite dimensional vector space, and then the last 3 define a subvariety of that. So we get the same type of theorem, which says that we get an algebraic quotient stack. I've just included here this kind of funny corollary, which just says that, I mean, if you look at the equations, it's definitely not, in the form here, it's definitely not coming from a Lie algebra acting on C3. You could ask, maybe we just found, we didn't choose the basis right. Maybe we can choose a basis such that it is a Lie algebra action. That turns out to not to be the case. And the way that you can prove this is, well, if it was written in this form, then by choosing a representation of this Lie algebra, you could get a flat connection. And you can put that into normal form. And this will be a flat connection of a very special type. So in addition to this system of equations, you'll get some additional equations, and you'll get some just huge system of equations which is overdetermined. And I kind of spent a day trying to find solutions, and it apparently has no solutions. Okay, are there any questions up to this point?
So how does this result compare to some cases the log function was I missed something.
Mm-hmm.
The objects here are holomorphic, analytic, or?
Holomorphic, everything's holomorphic.
Okay. Because in the smooth case, you have that it's a reaction algebra, no? At least in a neighborhood of the critical set, or?
I don't.
Well, and then the global construct. Well, yeah, I don't know.
I don't see why it would be, but I don't know.
Thank you.
Okay, so I want to kind of switch gears now. So for the rest of the talk, I just want to explain the proof of the normal form theorem, And I'm just, I mean, you can do it for kind of a general, so the way that you do it is that you take the log tangent bundle, you integrate it to a groupoid, and you study its representation theory. And you get to a class of groupoids that I'm calling homogeneous groupoids. And you have to kind of study their representation theory. So I just want to explain the case of the cusp singularity, because all the ingredients are present in that case, and it's very concrete. So that's what I want to talk about now, and there's kind of two results that I need to kind of explain. One of them is a linearization theorem, and one of them is a Jordan decomposition theorem. And yeah, maybe something that you can take away from this part of the talk is it's about actions of C, like the additive group C. So we all like actions of C star because they have a compact S1 inside that you can average over. And you might be worried that if you have an action of C, that things aren't so good, which is true in general. But if you can, what I want to kind of explain is that if you can kind of control your action, then it's basically as good as a C star action. Okay, so I want to go back to this cusp singularity and look at its Lie algebroid in more detail. So in this case, the log tangent bundle is an action algebroid I mean, this is a non-abelian Lie algebra. There's a unique one in 2 dimensions, and so this is acting on C2. So the first thing that I want to do is integrate this to a groupoid. So this is possible by a criterion of Crowell-Debar, because the anchor map for this Lie algebroid is generically injective. So we know that we can integrate it. And I want to take the source simply connected integration, and this is what's called the twisted fundamental groupoid. And you can think of it, kind of the first approximation is it's homotopy classes of paths in C2 that are tangent to this thing. So either they lie kind of in the complement, or they lie along the smooth part, or they're kind of stuck at this point. It's not completely accurate, but I think it's a good way of thinking about it. Okay, and the reason that it's useful to look at this groupoid is because of Lie's theorem for Lie groupoids, which says that flat connections, or in other words, representations of this Lie algebroid, they're equivalent to representations of this groupoid, which you can just think as homomorphisms from this groupoid to GLN. So we can kind of, instead of studying flat connections, we can move to this setting and study these things. So that's what we're going to do. Okay, so you might expect that, I mean, the Lie algebroid is an action algebroid, so maybe the groupoid is also an action groupoid, but this is not the case. And the reason for it is quite interesting. It's vector field V, one of the generators, is not complete. And I kind of have a picture here of the situation. So this function that cuts out D, the curve, you can think of it as a map from C2 to C, and it defines a fibration. And it has a unique critical point, right? This point here, the cusp. So all the other fibers are smooth. And this thing, because it's a cubic curve, it defines a fibration by elliptic curves, by tori, complex tori. And because C2 is non-compact, these fibers, they can't be compact, so they're actually going to have a puncture. They're once punctured. So this is kind of a cartoon picture of the family. So in green is C2, and it's kind of a bundle of tori that kind of degenerates to the singular one, and in red, this is like the points that have been removed. And the vector field, this algebroid is like the symmetries of this family. E is kind of the thing that lifts the scalar multiplication on the base, and V, it points along the fibers. And it's non-vanishing. So it's a non-vanishing vector field on a complex torus. And we've removed a point that can't be complete. Okay, so we could try to fix the problem by adding in these points. So we can kind of compactify the family to get some space X, and then it works. We do get an action groupoid. And then we could take this groupoid and just restrict it back to C2, and that will give us a perfectly good Lie groupoid that integrates the Lie algebroid. But it won't be the right one, right? Because the fundamental group of D in X and a D in C2, they're not the same, right? In one case, you have a torus fibration over C2, or sorry, a torus fibration over C star. So the fundamental group is semi-direct product of Z on Z2. But in the other case, it's a bundle of punctured tori over C star. So the fundamental group is the semi-direct product of Z with a free group. Okay, so that's what's going on. But if you want, just take the Weinstein groupoid, the universal cover of this thing. Okay, so the groupoid is not an action groupoid. And that's because the vector field V is not complete. The vector field E is complete, and so it defines actually an action groupoid. And so that means that sitting inside of this twisted fundamental groupoid, we have this sub-action groupoid. This is kind of crucial for understanding the representations. So here I've kind of written a point in here as lambda xy, and it's the action is given by the flow of the vector field E. So it takes xy to, well, you multiply with weight 3 on x and with weight 2 on y. Sitting inside of this groupoid are the isotropy elements. Those are the paths that kind of start from a point and go back to itself. So that's this copy of Z times C2. And you can really think of these as kind of they're loops. They're kind of loops that kind of wind around D. And the key thing about this groupoid, is that it's central. What I mean by central, I've illustrated in the picture. So here, gamma is a path. It's an element of this groupoid that goes from x to y. If I have the point 1, I can either consider it as a loop starting at x or a loop starting at y, and I can do either composition. I could do gamma times like 1, or I realized that x and y was not the right, maybe I'll call it P1 and P2. That's the equation that's satisfied. And actually, the proof is also in this picture, right? We have this action of C, so if we have this path gamma, we can use the action of C to kind of sweep out a cylinder, right? And then it's kind of clear the homotopies, you just slide this loop across. Okay, so yeah, so I said this subgroupoid is important, and the reason, well, so whenever you have a morphism of groupoids, you can pull back representations. So you have this functor from the category of representations of this to the category of representations of this action groupoid. It's just if you have a homomorphism, you just restrict it. You can also do this for the subgroupoid of isotropies, and this gives what I'm calling the monodromy. So if we take this kind of loop 1 that kind of goes around, we can kind of consider it kind of varying around the whole space, and we can evaluate a representation on that, right? And that gives us a family of a holomorphically varying family of matrices. And you can think of that as like the parallel transport of the connection around these loops. And the key fact is that because this subgroupoid was central, M is an automorphism of the representation. So it's a very important fact. Whenever you have a representation of one of these groupoids, you get for free an automorphism of it. And this automorphism is kind of telling you something important about the representation. Okay, so this is, I think, the setup that I want to give. So now I want to explain the first result, which is linearization. So the goal is that we start with a representation, we pull it back to this action groupoid, and we want to linearize it. So first, what do we mean? So for this, I want to explain, we have some more morphisms of groupoids. So this is very simple. Maybe I'll just, we have C, we have C action C2. We can either just project to lambda, or if we have lambda, we can include it as belonging over 0. And those two morphisms will give us these functors. And so what we can do is we can take a representation of this action groupoid, pull it back to a representation of C. So now this is very simple, right? A representation of C is just specified by a matrix. And then we pull it back by P. So this composition gives us a functor, which takes a representation and spits out a very simple one, which I'm calling the linear approximation. And a linearization is an isomorphism from psi to L psi, to the linear approximation. So you can imagine if we want to get these normal form theorems, we want to basically write the representation in as simplest form as possible. This is like the target that we're aiming for. Okay. So in general, these things don't exist, and the reason is the monodromy. So I said the monodromy tells you something important. It actually tells you about the failure of linearizability. And the reason for this is also very simple. So if we take a representation, we look at its linear approximation. Remember, it's just specified by a matrix. Okay, so it looks like something like this. And so the monodromy will be constant, right? It will just be exponential of 2 pi ia. So now if we had a linearization, well, that means that the monodromies are going to be related. They're going to be related by conjugation. And so that means that M of xy lies in a unique conjugacy class. And that's a restriction. In general, it won't be true. Right? What's true, you have the orbits of this action, the flow of the vector field E. You get these kind of orbits, they all limit to this point. And along a single orbit, right, the monodromy is going to remain in a single conjugacy class. Basically because the representation, it kind of conjugates the monodromy from one point to the other. So along these paths, the monodromy remains. But, once it gets here, it will only go into the closure. And there's no reason why this one and this one, it will be in the same conjugacy class. They just have the property that their closures meet. Okay. And this turns out to be the only thing that obstructs linearizations. So a representation of this groupoid, it can be linearized if and only if the monodromy lies in a unique conjugacy class. So as you vary over the entire space, you just lie in a unique conjugacy class. And this has this, this I don't care about actually. This is the thing I care about, which is that a representation, it can be linearized if it has semi-simple monodromy. And the reason for this is because the conjugacy classes of semi-simple elements are closed. So if you follow this thing here, right, you're going to stay in the same conjugacy class. All the orbits limit to this point. So that forces that the conjugacy class of all orbits is the same. So for semi-simple, this hypothesis is satisfied, and so we can get a linearization. So I'll just try to go through the proof. I think I have time. It's not, yeah. It will be kind of a sketch. So given a representation, we want to find a linear, we let this be the linear approximation. And the goal is to find an isomorphism between these two. And very concretely, this is a holomorphic matrix that satisfies this equation, right? It intertwines the two representations. So I want to reformulate this. I want to take this thing and move it to that side with an inverse. And then we can think of G as being kind of satisfying some invariance property. So we can define an action of C on this trivial bundle, C2 cross GLN, which is, it's kind of like a conjugation, but I'm acting on the left by the representation and on the right by the linear approximation. A linearization, right, if you rearrange this formula, you can see it's nothing but an invariant section for this action. Okay, so here's how we can do it. So I'm going to use, for step one, I'm going to use the hypothesis that the monodromy is in a single conjugacy class. That means that I can find a gauge transformation that makes it constant. At least we can do it locally, which is good enough. But let's just assume that we can do it on all of C2, just for simplicity. So, and we're going to choose it to be constant and equal to the monodromy of the linear approximation. Okay, so now the monodromy M is constant. step 2, let C be the centralizer. Because M, which is now constant, is an automorphism of the representation, that means that the representation must lie into this centralizer. So that means that this action, it actually acts on this smaller subbundle, C2 cross C. And now this action is very good, because if you look at what happens when we plug in lambda equals to 2 pi I, well, here we get the monodromy, here we get the inverse monodromy, right? M inverse, and G, it commutes, so they cancel. So that means that this action descends to C star, right? And now we can just apply what we know about C star actions, right? They're very nice. So we can do kind of we have a fixed point, which is, say, the point over the origin in C2, and we have the identity matrix. That's certainly in the centralizer. So this is a fixed point, and we can linearize the action of C star around this point. And so what we get is a representation of C star. And it sits in a short exact sequence, right? Because this fiber over 0 is preserved by the action, so that gives us a sub-representation when we linearize. And this projection map, I kind of chose this action to be so that the projection is equivariant. And so this map is also a map of representations where C2 is the representation that I started off with. So now we have just a short exact sequence of representations of C star, and we can split this, right? So here I drew the splitting, right? And a splitting, that's nothing but an invariant section. So that's how we get it. Okay, so just to recap, we have a representation. We pull it back to this action groupoid, and we want to linearize it. And we saw that this, it can't happen in general because of the monodromy. But we saw if the monodromy is semi-simple, it's okay. So the obstruction is the unipotent part, kind of the other part of the monodromy. So what we want to do, we don't like this part, so we just want to remove it. So we want to deform the representation in order to make the monodromy semi-simple. So in order to do this, I just want to kind of briefly tell you about cocycles. So if we're given, so G is an arbitrary groupoid. I don't know why I took a different one, but we take a representation, then a cocycle, a one cocycle is a map from the groupoid to GLN, such that if you multiply it with your representation, you get a new representation. So if you want, you can expand what that means and get a cocycle condition, but this is what the meaning is. Okay, so what I want to explain is a construction that, so what is a zero cocycle? A zero cocycle is an automorphism of a representation. A one cocycle is a deformation of a representation. So I want to explain a construction that allows you to move from zero cocycle to one cocycle. So from automorphisms to deformations. And this is the following construction. So it's kind of very general. So let K be a Lie group. Let pi be a homomorphism from our given groupoids to K. And then given a representation, suppose that we have a homomorphism from our group to the group of automorphisms of the representation. Then this formula defines a cocycle. We just take an element of G, we map it with pi to K, we map it with C to automorphisms, and then we evaluate it at the target of G. You can check, it's just a simple calculation. This thing defines one cocycle. So I want to basically get this setup in our situation. So the first thing to explain is, what is this map pi? So let's go back to this equation. So remember, we have this function that cuts out d. And the lemma, which is, it's not difficult, it's just that if you take the logarithm and you pull it back by target and source to the groupoid, this gives a well-defined homomorphism. And this homomorphism, it has the property that if you pull it back by R, it's just the projection map. So maybe it's It'd be good to put it on the board. Okay, so that, remember, this was the first thing that we needed. The second thing that we need is a homomorphism from C to the automorphisms of a given representation. And we almost have this, right? We have the monodromy, right? The monodromy, though, is a map from Z to the automorphisms. So let me just put this here. So we want this. I mean, this, yeah. So this is basically the last thing I need to explain is, well, we can't quite get this, but we're going to get something that's good enough. And for this, I just need to recall the Jordan decomposition. So the Jordan decomposition is just something that exists for matrices. It just says if you have an invertible matrix, it has a unique factorization. M is equal to SU, where S is diagonalizable, U is unipotent. So if you forget what this means, it just means that U minus the identity raised to a high enough power is 0. And SU and US commute. So maybe you're more familiar with the additive Jordan decomposition, which is for any matrices, you can write it as the sum of semisimple plus nilpotent. This is the kind of the multiplicative version, semisimple times unipotent. And on the unipotence, the logarithm is well defined and algebraic, right? Because you just write the Taylor series. And this thing, I mean, by assumption, it vanishes for high enough k. So this is a polynomial. Okay, so I want to now apply this to the monodromy of a representation. And this is the following lemma. So if we have a monodromy, we take its unipotent part, U, and it turns out that this defines an automorphism of the representation. So it varies smoothly, and it's an automorphism. And we can now use this. I mean, now because we have the logarithm, we can use this to extend the map. So instead of M, I'm going to put U inverse. It's a homomorphism from here. And this we can extend. And the reason we can extend is we can take the logarithm. Right? So it's this formula here. Take the logarithm of U, and then multiply by Z and exponentiate. And that gives us this extension here. And this lets us apply the Cocycle construction. So given a representation, we build this Cocycle, and this gives us a new representation. I think I didn't have a slide for this. I should have put this, but I mean, the key fact is that if you look at the monodromy of this, it's kind of cooked up so that the contribution to the monodromy from this thing is U inverse. So that means that the total monodromy is U inverse times U times S, which is S. So this deformed representation, it has semisimple monodromy. And this, I mean, it's kind of a very functorial procedure. So you actually get an equivalence of categories. It's actually an isomorphism of categories. So there's an equivalence between representations of this twisted fundamental groupoid in this category that I'm calling JC for Jordan-Chevalley. And the objects are just tuples, a representation of the groupoid with semisimple monodromy and a unipotent automorphism. The map is that we just extract the semisimple part, and then we just keep the unipotent part of the monodromy, which is an automorphism. And this is, remember at the beginning I told you about this result of Levelt from the 70s. So this is a way to generalize it and kind of reformulate it using Lie groupoids. Okay, so basically, we just need to put all of the pieces together, and this will give the proof of the normal form theorem. Right, so we start with a flat connection with log singularities. Step 1, we integrate it to a representation of the twisted fundamental groupoid. Step 2, we factorize it using the Jordan decomposition. Then we can take the semi-simple part and restrict it to this subgroupoid. And this thing, it can be linearized because it has semi-simple monodromy. So we get this gauge transformation. And my claim, which it's not difficult to check, is that if we apply this gauge transformation, then this resulting connection will be in the normal form. OK, so that's all I had. Thank you.
Are there more questions for Francis?
Thank you for the great talk. I'm thinking by analogy, in complex dimension 2, with this divisor, do you expect the moduli space to have a Poisson structure? I'm thinking by analogy of real dimension 2 with boundary. And in that case, would these linearization theorems tell you something about the...
So yeah, that's my hope. I mean, I have all of these examples of the spaces now, but I haven't really started to study their geometry. But that's my hope. And something about this example of this this thing. This is in C3, or sorry, C2, which is R4. We can kind of intersect it with S3. This intersection is the trefoil knot. So kind of C2 minus D is homotopic to the trefoil knot complement. And in fact, I mean, the only thing that's different is this point here. But it turns out that the representations, the category of representations where you include this point in your space are not their equivalent. So, yeah, I don't know. Maybe it's related to this. I mean, I've been looking at this, but just very recently.
Yeah. Is it possible to hear me? No? So you showed this 17 surfaces in the beginning. I have a kind of an outlandish question. So 17 is not a constant that I see every day.
Sorry?
Sorry. So you've shown the 17 surfaces in the very beginning.
Oh, yeah.
And I have an outlandish question about it. So 17 is not a constant that I see every day.
Yeah.
But there's this one context in which it appears. Do you know why there are 17 of those, or is there any good explanation for it?
No, I have no idea. But I just thought it would be nice to maybe just put up the family again. But yeah, good question. I don't know.
Thanks.
I also have a very brave question. So can you understand this B symplectic, or is there an interpretation of this B tangent bundle or B symplectic or log tangent bundle in the derived setting?
In the derived setting?
Usually it looks like it's just a set bundle of tangent bundle, right? Can you really interpret it as a complex?
Yeah, I'm not sure, but yeah, that's a good point.
OK, let's thank our speaker again. And this is all for this morning. Thank you very much.